Hi, good afternoon, everybody, and welcome to this new lecture on access control or introduction to access control. Um, so today we will look at the idea of access control and what it means and what it does in terms of computer security. And then we will look at a few models of access control that have classically been there for a long time, and they give us a sort of fundamental or basic understanding of what access control is and help demonstrate what it does for our computer security. So we will look at things like access control lists, discretionary mandatory access control, multi-level security classifications, and we will also touch on a couple of examples of security or access control security policies, BLP and Biba. So first of all, what is access control? Access control is the process of defining and managing and enforcing the rights and permissions a resource has in some computing system. So the idea is that you want to define exactly what are the rules, or what kind of way can different users use your resources in a system, and then you define how those rights that you're assigning will be enforced in that system. Access control is fundamental for authorization. It requires authorization. So the idea that you will then help make the decision as to whether those sort of users can access your resources, that process is called authorization. Authorization and access control, both of them are based on authentication. Okay, so what we studied so far in terms of authentication protocols um, essentially form the basis or an important building brick for authorization. Without authentication, you can't really achieve authorization. So let's have a look at the uh, first starts of access control and where did it essentially come from. So if we go all the way back to 1972, we find that this concept was introduced by someone called James Anderson at the time, and he essentially defined this kind of sort of model or concept to protect resources which exist in a machine, in a single computer. Okay, so the idea there was that you want to protect your hardware from the from any software or from any applications or um, processes that the users um, use to access that hardware. And the idea is that your hardware is an important resource for yourself, whereas the software and the applications and so on, they're untrusted. Okay, so they can be defined and run by any user, and so therefore you cannot really trust them. So James Anderson wanted to define a solution that would protect the precious resources from the untrusted user processes. Okay, and his model was what came to be known as the reference monitor. Okay, so the reference monitor is everything which is within this box here, and it consists of three uh, important concepts. The first one is the logic itself, or what we call the reference monitor itself. So this is the engine that helps reach a decision as to whether a particular request for access by process to some hardware should be granted or not. And this decision is not done just in an ad hoc way. It is done based on what we call a security policy and all security policies are stored within some kind of a security policy database. Then, of course, you would want to also log everything and try to ensure that every activity is logged, and that constitutes the third part of this architecture, which is called or was called audit trail. Okay, so this is basically a log of all the activities, everything that is going on across this isolating middle layer. So this was essentially the starting point of access control, and very much even nowadays, most of the solutions we used are a variation or another of this kind of architecture. So the fundamental idea has not changed. It has sometimes become a bit more complicated, especially when we will look later in the module at things like federated access control um, and federated authorization, but essentially at the simple level of your operating system, um, or even at your local network level, the same concept or the same idea remains even in use nowadays. So here are some examples of reference monitors you could find in the real world. If you look at operating systems, the kernel, which is operated by your operating system, is in fact an example of this reference monitor. So it's got within it the ability to determine if certain requests for access to your local folders, files, local essentially directory system should be or shouldn't be allowed according to well-defined or predefined security policies. If you are looking at the level of a network, then you can think of a firewall, for example, as a good example of a reference monitor. So again, it's the same idea. A firewall isolates the inside of a network, which is trusted, from the outside of the network, which is the outside world, which we assume is not trusted. And of course, things like VPN and so on allow us to access the inside world in a secure way. But all those are essentially what they're doing is that they're attempting to find a tunnel through this isolating layer, which we call a firewall. And as I mentioned just a few seconds ago, you then can move up to federated identity management and federated authorization. So you have things like XACML enforcement points and OAuth servers and stuff like that. Those again are complications from this thing that we call a reference monitor, which act at a more global or as a more global solution. Right, so before we delve into the few models of access control for the rest of the lecture, let's have a quick overview of the terminology we're going to be using from now onwards. These are a few terms that you need to keep in mind as we go forward. So first of all, the term subjects. We use the term subjects to refer to any users, whether they're humans or machines or applications, or even groups of users. Okay, so these are the entities that are doing something. Okay, so they're applying some action to our resources. On the other hand, the resources themselves can be we call them here objects. So these can be things like your files, your printers, your storage space, any processors, computational power you have that you need to use. Again, all of these you can think of them as being objects. Then, as we said, objects perform actions on objects, but these actions they need to be permitted, okay, and sometimes they're not permitted. So the thing that permits the actions to take place is what we call a permission. Okay, so a permission is the right that you're giving to the subject to allow that subject to access a particular or a specific object. So the permissions that we are mostly interested in are things like reading a file, writing to a file, executing a file, appending to a file, opening a file or a folder, and deleting a file or a folder. If you're talking in terms of the storage system, of course, if we are talking in terms of a network activities, then a very simple example of the permissions that a software could have are things like sending a message or receiving a message, or the ability to write to some shared space or amend and so on. Finally, we call the set of rules that determines which permissions can be applied by which subjects on which objects. We call these our security policies. Okay, so security policies are essentially the way you are wiring your rules, the way you are expressing how essentially how um, subjects can access objects and so on. Right, so let's move on to the first simple model, the most basic model that is quite often used in our operating systems, and this is known as access control lists. Okay, so the idea of an access control list, as the name suggests, is that it is a list. Okay, so a list is an ordered set of items. Okay, and it has the simple form. Okay, so this is the form of the list. It consists of the following things. Okay, so first of all, you have an object. Okay, so this is the name of your file or folder, and then associated with that is a set of pairs, and inside each of those pairs you have the name of the subject that can access this object and a set of permissions with which the subject can access the object. Okay, so this symbol here is a symbol of a power set, meaning that the element there is some kind of set of these things. Okay, so here's an example of how you could express an access control list. Okay, so here is the name of your object. So it could be file 1, file 2, file 3, program 1, whatever object or whatever resource you have, printer 1 or whatever. And then associated with that is a set of users. Okay, so you have Anne, Bob, and Carl, Bob, and Carl, you know, whatever set of users you want to associate with that particular object. And for each of those users, you have a set of permissions. Okay, so for example, in this case, Anne has the permissions to read, write, and the ownership permission to file 1. Okay, so that means basically that Anne owns file 1. So she probably can open it, delete it. She has created it initially, and so on. Whereas on the other hand, Bob, as you can see, has only the read permission to that file 1. And we often write it in this way because this is sort of a linked list way. Okay, so at the end of each user, you can link to the next user and so on. Okay, but it's not necessarily strictly. I mean, this is only one form of basically implementing an access control list. The more kind of frequent way of implementing it is as a matrix. Okay, so again, you have your basically names of your rows, and these represents the user, you or users who will have access to your system resources, and the names of your columns represent the names of those resources that are existing at the moment in your system. So again, you have similar information here. So you have Anne accessing file 1, accessing file 2 with certain permissions. She has no access to file 3 because, as we saw here, there was nothing saying that Anne can access file 3, for example. So we leave that intersection as empty, and so on. Okay. So that's the idea of a essentially an access control list, expressed this time not as a list but more like a matrix. Now, moving on, we go into what we call discretionary access control, or DAC models. Okay, so DAC models are not really as strictly as such models of access control. They're more kind of way that you would want the policy in your system to be controlled and defined. And in a discretionary access control based model or system, the owners are the ones, or the owners of the resources are the ones who have complete control over the resources. Okay, so in other words, the control is localized for the owners. And a very famous example of that is Linux. If you've ever installed Linux on your any of your machines, then the Linux file system permissions are an excellent example of a discretionary access control. And the reason is because you as an owner have complete control over the permissions that you give to your files and folders and so on, and you can change those permissions via the chmod command. So there's some examples of the chmod command, how it works. So if you essentially give it a certain number, that number it gets translated to the different permissions that are to be given or not to be given to your to a particular file or folder that you're using to set. Okay, so essentially you can do that for not just the individual users, but you can do that for groups of users and for anyone who is outside your groups and outside the administration of that network or system. So each of these essentially permissions, the read, write, and execute, have got a number. So the read is number 4, write is number 2, and execute is number 1, and that comes from their binary position. So if you wanted to set a particular permission, say if I wanted to just set the write permission, then I would do chmod 400. Okay. If I wanted to set all 3 of them, I would do chmod. Sorry, not 400, but in that case 4. In this case, I would do 7. Okay, and I have to do that for all the other 2, all of these 3 parts or groups of users. Okay, so if I wanted to give just the read permission to all the users and nothing to groups and nothing to others, then I would specify 400. So that's 4, and this would be 0, and this would be 0. So then it becomes 400. Okay, and if I wanted to give the read permission and the execute permission to groups and execute permission to others, then that becomes 411, for example. Okay. You can get more detail on the chmod and how it works in some other outside resources. On any reference on Linux, you can consult it and get more sort of detail on chmod. But the idea is that it's that you, as the owner of the file, have complete access on how you want, or complete control on how you want to set the access rights to that resource. Windows does the same thing, except with Windows you've got something called a discretionary access control list, or DACL. So for every user in the system, or every subject in the system, you specify what that subject can or cannot do, essentially, on that particular object. Okay, so when the subject attempts to access the object, the Windows security kernel will look at the what we call an access control entry point for or every access control entry point in that discretionary access control list, and will determine if one of those access control entries actually permits the attempt of access by that subject to that object. Okay, so if that's the case, then it will grant the access to the subject, to whatever the subject was requesting to do to that object. If none of these entries satisfies the query, then the system comes back saying, sorry, you're not allowed to perform this access. Now, at some point in time, there was an attempt to turn this into a more kind of a programmatic way. So few people, Harrison, Ruzzo, and Ullman, came up with what's known as the Harrison, Ruzzo, Ullman model of discretionary access control, in which they attempted to program or define some kind of a programming language, or a pseudocode programming language, in order to allow us to change the access control matrix according to to our policies. Okay, so the idea was that you define some kind of command like this one, where you give the command a number of inputs. Okay, so that's the information that will go through, and essentially you would check if a certain entry was in your access control matrix, or a certain permission there. Then you could apply some operations. Okay, so you check for a number of conditions first. Okay, and if those conditions are satisfied, then you apply some operations. So it's like an if-then kind of command, or if-then pseudo language, let's say, if-then else pseudo language, except there is no else here. So an example, or one example, would be the following, which allows us to create a file. Okay, so this is a command for creating a file. So you create a file F, and then you enter in the cross section of S and F, where S is the subject creating the file. You enter the following permissions, and those are basically the ownership, the ability to read, and the ability to write. Okay, so what this will do is that it will, going back to our matrix, it will create an entry here saying that subject X now owns the specific file with the ownership, reading and writing permissions. Okay, so that's what this kind of command would do. Other example commands include granting the read access and revoking the read access. So in this case, if you wanted to grant the read access and you were indeed the owner of a particular file, okay, then you can give the read access to some other subject S prime to that file. Okay, so that would be similar here. For example, if Bob wanted to grant the read access to file 1 to Carl, for example, although, well, they're not the owners. Let's take the example of Anne. Okay, so if Anne wanted to grant the read right to Carl to read file 1, then she can execute the grant read command, and that will insert the permission here, which is the permission, the read permission for Carl. Okay, so that's because Anne owns file 1. Okay. Similarly, revoking can be done similarly, same way. So if you are the owner, you can revoke the read permissions. So for example, Anne, who is the owner of file 1, if she wanted to revoke the read permission from Bob, she can execute the revoke read command, and that will generate a new matrix in which the read access is or the read permission is not there for Bob. Okay, so Bob will have an empty box here essentially. Right, so that's discretionary access control. The idea of it is that you have complete discretion in how you want to grant access to the files and the resources that you own. Now, there is a strict model called mandatory access control, and that generated or was first proposed and implemented in military systems and military institutions. And the reason is because it is quite rigid. Okay, so it's quite strict. You cannot change a policy as you wish, but the policy is set by some kind of a centralized administration unit or centralized administration office. Okay, and so therefore it implements the concept or the philosophy of a system-wide policy. Okay, so rather than having localized policies which are controlled by the owners of resources. In this case, there is somebody sitting in an office, in a centralized office, administration office, who controls everything. So you have a control command unit, let's say. So it is, as I said, very popular in the domain of military security due to its strictness and rigidity, and that kind of strictness and rigidity is indeed necessary for highly critical systems such as military and defense systems. It has been always associated with multi-level security, although it's not the same thing, but they go hand in hand. Okay, so multi-level security goes hand in hand with mandatory access control. Of course, a very famous example of multi-level security is this sort of classification systems that we use. For example, for classifying our documents. So you have this kind of system that classifies documents as either unclassified, confidential, secret, or top secret. And there are other, similarly other, maybe with different terminology, but they're the same kind of a concept for classifying documents or sensitive documents. But if we wanted to be more kind of generic and more kind of rigid, well, not rigid, but more robust about how we express the concept of multi-level security, we have to go back to its mathematical roots. And the idea of an MLS policy or multi-level security policy is the presence of something we call a partial ordering relation. Okay, so partial ordering relation is any mathematical relation that can be used to compare things. Okay, so if you wanted to say that one level L1 was less important than another level L2, then that would be an ordering or a partial ordering relation. Okay, of course it's partial because not everything is comparable. Okay, so there are some things you can't compare them to some other things, and similarly, if you're talking about security levels, there are some security levels that you cannot compare with other security levels, and therefore it is a partial ordering relation. So don't worry about this part here, but it's just essentially saying that such a relation would have certain properties associated with it mathematically. So it's reflexive, transitive, and antisymmetric. Okay, which makes it essentially an ordering relation. But don't worry much about that. However, what we are interested in to know is that using, or if we have this kind of mathematical tool in our hands, we can build something called a lattice. Okay, so a lattice is a very useful structure because it allows us to, as we will see later, to define how we order our security levels in a more kind of an interesting and generic way. Basically, a lattice is any structure which has a top and a bottom elements for any two levels. Okay, so if you were to pick any two items or any two security levels, there is a common top for them and a common bottom. Okay, so this is an example here of a lattice. Okay, so if you pick any two elements here, they will have a common parent and a common child. So if you were to pick L1, L2, for example, their common parent is the top element here, and their common bottom element or is the bottom element here. If you were to pick L1 and T, or L1 and top, then the common top is the top and the common bottom is L1. Similarly for top and L2, the common top is the top element and the common bottom is the bottom element. So this renders this structure a lattice example. However, a more kind of interesting lattice is what we call the lattice of power sets. Okay, so power set is the set of all sets. Okay, so if I were to give you a set XYZ, then the power set of XYZ is all the subsets that you can construct from XYZ. And that includes the XYZ itself and the empty set. Okay, so there's a natural order here based on subset inclusion. So for example, the bottom element is lower than every other element. Okay, but if you took, for example, this set which consists of only the element y, then that is less than xy and x and yz, but it has no relationship to the subset which is x and z. Okay, so you can see these two are not comparable. Okay, because there is no subset inclusion between either of the two elements. And of course the top is the one that contains everything because it contains everything, so everything can be related to it. So xy, xz, yz relate or are less than this set. And of course don't forget that it is a transitive relation, meaning that if L1 is less than L2 then and L2 is less than L3, then naturally also L1 is less than L3. Okay, so we We don't need to draw a line between y and the top set here, because that line is an indirect one. So you can go via y to xyz, or via y to yz, and then xyz. Okay, so that is the transitivity property. And why are we so excited about this structure? The reason is because it gives us a very nice lattice. So if you were substituting your xyz, um, uh, you're substituting them for actual permissions, you see that the whole thing makes sense now, because you could assign a subject a top level classification like this one, read, write, and execute, and that person would be able to read, write, and execute every document in your system. Whereas if you assign a person this bottom level, which is the empty set of permissions, then they will naturally not be able to do anything in your system. And the same thing goes for objects. If you were to assign, for example, this low level or the empty set level classification to your object, to your document, then that would mean that that document, you cannot do anything on it. Okay, so it's the most sensitive object in your system. Whereas if an object had a classification assigned to it, which was read, write, and execute, then that would make it a not so sensitive object in the system, because simply you can perform anything you want to perform on that object. Okay, so in this current shape, and with this kind of ordering, going from the bottom element to the top element, it gives us two kind of semantics. Okay, so if you're talking about subjects being assigned these security levels, then if we go upwards here, we're going from the least permitted subject to the most permitted subject. However, if you are talking about using these levels as a classification for your documents, your resources, your objects in the system, then going from top to bottom means you're going from the least sensitive to the most sensitive objects. And that essentially is the idea of multi-level security. And of course, such classifications, so whether you're classifying subjects and objects, as I said earlier, it's something done by a system-wide policy administration point. Okay, so some kind of a control and command, or some kind of a security admin office who would set for each object and each subject in your system the appropriate security levels. Now, this is not, of course, ending here. So next we look at how this kind of classification can be used to determine exactly policies that protect our security. Okay, so we have a couple of examples here we call BLP and Biba, and we will see how BLP, for example, protects the secrecy of information in our systems and resources, whereas Biba protects the integrity of that information and the integrity of resources. So let's start first with BLP, or short for Bell-LaPadula policy. So these two guys, Bell and LaPadula, came up with this policy, which is based on multi-level security, in order to solve the problem of how can I protect information, sensitive information, being leaked out of my system. Okay, so or out of my resources. Okay, so they defined this policy in terms of two properties. Okay, so the first one is known as the simple security, or SS property, which dictates that you should never ever read upwards, or you shouldn't be allowed to read upwards. Okay, so if you are a subject, okay, and you're attempting to read an object, then you can only do so, i.e. read information or data from that object, and that includes also executing the object as a sort of a different way of reading stuff from it. Then you can only do that if the object was at a lower security classification than your security classification as a subject. Okay. And the other property is called the star property, and that dictates that you can never write downwards. Okay, so if you are again a subject and you're attempting to write some data to an object, then you can only do so if you are at a lower classification, security classification, compared to the object. Okay, so basically you cannot read upwards nor write downwards, and if you respect these two properties in your system, then according to the BLP policy, you will be guaranteeing that information will not leak. So information will always be moving from the low levels to the upper levels to the higher levels, and never the other way around. Okay, so you can your information will never be going downwards. It will only be going upwards. Okay, so this naturally helps secrecy. Okay, or what we sometimes refer to as preventing leakage. So here's an example, graphic example here of where you have a number of files classified at certain levels, top secret, secret, confidential, and unclassified. And here is a user process or application or software, or whatever you want to call it, and that's running at a level which is the secret level. So these arrows here demonstrate what that process can and cannot do to each file. Okay, so depending on the level of the file, it can either read or write, or only read or only write to those files, depending on the level of whether the level is higher or lower than the processor's level. So BLP protects secrecy by preventing information leakage. That's the idea of it. And at some point, another group of people came up with what is known as the BIBA policy, and that is essentially the reverse of the BLP policy. Okay, so the idea of the BIBA policy is that you want to protect the integrity rather than the sort of secrecy of your information. And in this case, again, you have your subjects and objects and your permissions, which are read-write permissions and security levels. And you again assign your objects and subjects certain security levels according to some kind of a lattice structure. So the BIBA property then states that you must respect the following two conditions in order for you to protect the integrity of your resources. Okay, so the idea here is, first of all, you don't read upwards. Okay, so sorry, you don't write upwards. So in this case, if you are a subject and you want to write to an object, then the object's level must be essentially lower than your level. And similarly, you can't read downwards, and that translates again in terms of the writing operation instead of the read. It translates as follows. So if you have a subject S, then that subject S can read an object O. Then S can have the write access only to objects which are lower than that level O. So essentially, the no read down is saying you can only write to objects that are lower than some object that you can have read access to. Okay, so you can think of these two properties in your head as properties that are trying to prevent clean high-level objects in your system, for example, your kernel, any sensitive parts in your operating system, any sensitive parts in your software or system or hardware system, firmware, whatever it is. They're trying to prevent those clean high-level objects from being corrupted by dirty low-level subjects or dirty low-level applications or user software, which is simply cannot be trusted. Okay, and this protection here is in terms or is in the sense of actually not corrupting those objects, so not writing to them, okay, and therefore not modifying them, because any modification cannot be trusted to preserve the function of those sensitive objects. Okay, so these two properties, in that sense, help us to protect the integrity of our sensitive resources. However, you have to notice here that BIBA doesn't give you secrecy. Okay, so these two properties, they don't protect the secrecy of your objects. Okay, in the same sense that BLP did not protect the integrity of objects. So each one of these two policies has its own distinctive functionality, which is different from the other policy. And here is as a final slide. Here is a diagram of again two processes. One is high level and one is low level, and two objects. One is high level, one is low level, and the arrows here demonstrate what each process can and cannot do to each of the two objects. And again here, as you can see, although it might be counterintuitive, but the high level process can write to a low level object. That's not a problem, because the purpose is not protecting against leakage of information. The purpose is protecting low level, or sorry, no, but protecting information and resources from being actually corrupted by processes. So if the process is more trusted than the file to which it's writing, then that's fine. You can use that process to write to the file. But if it's the other way around, so if the object is more trusted than your app or process or software, whatever it is, then you cannot do that. And the only thing that that process can do is actually just read information from the object, because reading does not change the content, only write changes the content. And by the way, the assumption here is that write does not imply read. Okay, so write is only writing, it's like a blind writing. Okay, it sounds a bit strange, but it does not imply read. Okay, so read, if you wanted to read, you have to specifically or explicitly request the read permission. The write permission is explicitly and only doing a write action. Okay, so it is not or it does not imply that you can read the file at the same time. Okay, that was all. Thank you for listening. Goodbye.